Yeah, yeah. Let me see if the picture is clear. Like here. Okay. Good morning, everyone. Okay, questions before I start. Good morning. Thank you, Christian. All right. Any questions before I start? All right. I'm going to start because are you guys getting the comments I'm putting on your quizzes? Are you reading them? Please say yes or no. Okay, great. So the solution will be, I forgot to put the solution yesterday. I will put it after class today. But I would like to make 2 comments about the quiz. The mistake that was very clear, a lot of students got it wrong, was question number 1 and the last questions. And the rest, you guys did fine. But it's the question number 1 which is important. And please ask questions I'm explaining because it's crucial. And the question was, we have the series sigma A sub n. And I told you that sigma c sub n is equal to 15. Okay, this sentence by itself means what to us? So you see, sigma is really. So you see sigma n equal 15, and it doesn't matter where we start. It means that A1 plus A2 plus A3 plus A4 plus dot equals 15. Again, what does this mean to us? What does this mean that the sum equals 15? Anybody would like to help me? Anybody? Mute and talk. All right, I'll talk. So this means the following. If I take the following sums, which sums? So if I take S1 equal A1, then I take this sequence, A1 plus A2. Then I take A1 plus A2 plus A3. And I keep doing this. S4, I add and add and add and add, and so on. If I keep adding those terms, what should we get as we keep adding them? As we keep adding them, so I keep adding those sums become close to 15. So to say that the series equals 15, it means that the sums, the Sn, the sequence of partial sums, is becoming close to 15. In particular, the series converges because it's getting close to a fixed number. So the sum Sn, so if equal 15, it means when we start adding, we get to 15. But if this is the case, what can we say about the individual terms, A1, A2, not the sum, those terms, A1, A2, A3, what happened to them when n becomes very large? Please, I need an answer. So the individual terms, A1, A2, A3, A4, what happened to those when n becomes large? Those terms have to become close to 0. So the individual terms go to 0, and that's crucial. So the answer to the first question was the partial sums become close to 15, and the individual terms, A sub n, become close to 0. Okay, so those terms, the terms by themselves, the sequence of terms become very small because, as we said last time, if the terms don't become very small, like become close to 1, I'm adding 1 plus 1 plus 1 plus 1, which is definitely go to infinity. So saying that the series sigma an equal 15 means that first the series converge, and 15 represent the partial sums, where the sums goes. It means when you add where you do. And the an, A should be equal to 0. All right, so that's the first question that actually you guys didn't do well. Now the second question you had difficulties with, not the geometry, those mistakes were corrected individually, but it was the last problem. It was number 4. Okay, and I remind you, it was the limit as n goes to infinity of 1 plus 0.8 to the power n, the whole thing divided by n. Now, in this case, what we are talking about is we're talking about a series. Sorry, my apology. Right here, I'm talking about a sequence, not a series. Some students confuse the series with the sequence. So here, the only thing I'm looking at is the following sequence. If n is 1, I'm looking at that. I'm not at all, then this, then that. So it's just a sequence of number. I am not adding them at all. That's what I am looking. So it's a comma. I am not adding those terms. I'm just looking at the sequence. I'm asking you what happened to those terms when n becomes very large. All right, the key thing here is the following. If I take 0.8 to the power n, this term by itself, when n becomes very large, this terms is equal to 0, mainly because 0.8 is less than 1. So let us have another look at this series. What is this, so we understand it? Why having 0.8 less than 1 will make this actually go to 0? Because let us analyze the sequence 0.8 to the power n. What is this sequence? The first term, 0.8. What's the second term? 0.8 squared. Now I'm going to ask you a simple question. Is the second term bigger or smaller than the first? I want an answer on chat. Is this one smaller or larger without computing? This one is smaller because what is this term? It's the original one. You're multiplying it by 0.8, which is a number less than 1. So you're multiplying 0.8 by something less than 1. The number is getting smaller. If you take 0.8 to the power 3, you're multiplying it by another terms less than 1. It's getting smaller, and so on and so forth. So 0.8 to the power n, because the number is less than 1, it gets less, smaller, and smaller. So that was the main thing here. So now what's going to be the limit? The limit now is not hard anymore. This term, 0.8, goes to 0. So now I have the numerator getting close to 0. Sorry, my apology. The numerator getting close to 1, because that's 1 plus 0. The denominator goes to infinity. So this is going to, the whole thing now is going to become close to 1 over something very large is something very small. Okay, so those are the two questions that the class as a whole struggled with. All right, so before I move on to the new material, I want to ask you a following question, and I want an answer. Simple, I hope. So, true or false? I'll pick up another paper. Question is true or false? True, you justify. False, you give me an example. Convince me it is false. Suppose you have a series sigma an. If the limit as n tends to infinity of an equal to 0. So I'm having the series sigma an, which means in my mind all the time I have adding terms, and see what happens as we add more terms. That's a series for me. So if the limit of an equal to 0, then the series converges. True or false? True, you tell me why. False, you give me an example. I'm expecting answer from you. You have a minute to answer. All right, who's ready? Christian, tell me false. Anybody else? False. Okay, anybody else? Anybody would like to tell me true? Okay, absolutely false. Absolutely false. If the terms become close to 0, we cannot at all say that the series converges. False, because we're going to take the series sigma an, which is, so we're going to take an to be 1 over n. So sigma an is sigma 1 over n. It means 1 plus a half plus a third plus etc. Now here, the an, it means those individual terms goes to 0. But the series sigma 1 over n sigma 1 over n diverges because it's a P series with P equal to 1. So if the terms go to 0, there is nothing we can say about the series. It can go either way. So it can converge or diverge. But when we say a statement, if the limit equal to 0, then sigma a n converge, it means is it true for every series? And the question is no. It's not true all the time because that's an example. So knowing the terms become small, no conclusion about the series as a whole. All right. Any questions before I move on? All right, today we're gonna see two tests. The first test, we're gonna call it comparison test. And this test is usually hard to use. It's important theoretically, and it's important for you to know. So, but before that, let me make a small comment that the tests we've seen so far are also always true only for series with positive terms. And the test we're going to see right now is also true for when the series have positive terms. And you guys will be asked to give me an example to show me that it failed when it's not the case. But first, let me state the integral, the ordinary comparison, and then give you an example how it works. So, section 11.4. The ordinary comparison test. The first test we saw is what's called the limit comparison. It means we compare my series in this to another one. Now, the ordinary comparison is slightly different. It tells me the following. Suppose I have two series, sigma an and sigma bn, and they are both series with positive terms. And assume that every term here is less than every term here. So A1 less than B1, A2 less than B2, A3 less than B3. And in general, AN is less than BN. So I have the following scenario in front of me. So I have the following scenario. So I have a series sigma AN, A1 plus A2 plus A3 plus so on. And B1 plus B2 plus B3, so on. Each A1 is less than that. So that's really what is going on. So intuitively, A1 plus A2 plus A3 plus dot, dot, dot that's very intuitive. Then plus B3 plus B3. That's really, everything is positive. So suppose I have that. So now my question is, if sigma bn converges, means when I add those, I get somewhere. Then what happened? The ordinary comparison test tells me that in this case, sigma an will converge as well. So if the larger series, if the sum of the terms of the larger series become close to a number, the sum of the term of the smaller one will also have to converge. So that's the first part of it. The second part of it tells me that if the small ones, means when I add the an, those diverges, means when I start adding a1 plus a2 plus a3 and those term goes to plus infinity, then the larger series will diverge as well. So the comparison test tells me the following, and that's exactly what the statement. If the larger series converge, means when I add the bn, we get close to a number, the smaller one will also converge, they cannot blow up. And then if the smaller one diverge, if adding the an, this will diverge, adding the bn will also diverge. So that's what the ordinary comparison test is telling us. So first let us say example, how to use it, and then we proceed. So my first example is the following. I put the example and then I look at it. All right, example 1. Use the ordinary comparison test to decide if the series converge or diverge. My series is cosine square n over n squared. And here I told you that, note that the integral test and the limit comparison tests are hard to apply. Why? The limit comparison would tell me, sorry, the integral tell me you have to integrate cosine square x over x squared. And it has to tell me that this function is decreasing. None of them is satisfied. Even integration is very hard to do. What about the limit comparison? What's the problem with the limit comparison? Can anybody point out the problem? What shall I compare it with? To make sure that you understand where the difficulty is. What shall I compare it with? The denominator is n squared. What about the numerator? What can I compare it to? Anyone? It doesn't simplify. Yeah, it doesn't simplify because cosine square, when n is large, is not close to anything. The reason is, if you guys remember, the cosine keep going up, down, up, down, up, down. So the cosine is not getting close to anything when n is large. So I don't know its behavior when n is large. So I'm stuck in this case. So I cannot compare it to anything by using the limit comparison test. However, the ordinary comparison test can be used. So what can I make this this series less than? So cosine square x over n squared. What can I make it less? First of all, this is positive. It's less than what that is hopeful. Now, whenever we see cosine, and something should really come to our mind. The cosine is always less than 1. It oscillates between -1 and 1, but it's always less than 1. So cosine squared over n squared is going to be always less than 1 over n squared, regardless what n is. So the cosine squared is not 1, is not close to 1 at all because it oscillates, but it's bounded above by 1. It's less than 1. So how I'm going to use the ordinary comparison test? I'm going to take this to be my Bn. I'm not using the limit. I'm using the fact that it's less than. And this is going to tell me that, so cosine squared n, which is my An, is less than my Bn, and they are all positive. So the ordinary comparison tells me if the larger converge, then you can conclude that the smaller converge. But do we have that? Let's look at the larger series, 1 over n squared. This one absolutely converges because it's a p series with p equal to 2. So the larger series converge. So by the ordinary comparison, the smaller one will converge as well. Okay, so that's how we can use it. This is a test, not easy to use because you have to show some kind of inequality, but it is useful actually a lot. All right, so it tells me that exactly what I said. If you can find this, another series that you can use to compare it with, you can do it. I'm going to do another example along those lines. And this one, I'm going to give you a few minutes also to try to interact with it. So I will not do the example which is on the note. I'm going to do another one because I want you to think about it with me tiny bit. So my second example is the following. I'm going to look at the following series. Sigma, let me start a new piece of paper. Okay. Sigma 1 over n minus 1. And I cannot start it at 1. I'm going to start it from 2 to infinity. And before we ask you anything, I'm going to ask you a question. If I give you this simple problem, I tell you, does the series converge or diverge? How would you do it? I'm listening. I'm reading and listening, everything you want. So sigma 1 over n minus 1, my question to you, does the series converge or diverge? I want ideas. How would you approach this problem? Anybody? Integration test, that's compared to 1 over n. I have two very good answers. So we can do it two ways. All right, so the first way is we look at the integral of 1 over x minus 1 dx. Now, because n starts from 2, my integral will have to go from 2 to infinity. We can do it this way, and this is going to give me the limit of ln of x minus y between 2 and t as t goes to infinity, and this will be equal to infinity. That's one approach. The second approach is, as your other classmate said, 1 over n minus 1. We're going to use the limit. As n is large, it's 1 over n. Sigma 1 over n diverge, sigma 1 over n minus 1 diverge. So these are two approaches to this problem. Today, I want you to do it in another way, just to emphasize a point. And I want to ask you, show that this one diverges using the ordinary comparison test. Okay, I want you to show it diverge using the ordinary comparison test. So what should we be looking for in this particular scenario? Please, I would like your answers. I cannot talk to myself. Okay, so I want you to convince me that this one diverges using the ordinary comparison. So what do you go after? You want a series which is bigger than it or less than it? Right, you need something which is greater than an. So greater than an, it means you want an. So the students are telling me you need something greater than an. It means you want, oh, no, she wants something greater. Am I writing it correct, Sarah? What do we want? So we want something here or something here, 1 or 2. Which one do we want? Scenario 1 or scenario 2 to show its diversion? Just put on your chat which one you want. Okay, so I want scenario 1. So we want this one because we want this to diverge. So we want something less than it which diverge. Now, do we have that? Yeah, absolutely, absolutely. Do we have that? All right, let's see if we have it. And 1 over n, of course, that's what we're gonna go after. Is this true? Is 1 over n less than 1 over n minus 1? Is this correct? Because the denominator is larger. So 1 over it, Sarah, tell me no. Let's see. N minus 1 is less than n. Am I right? So when I flip them, what happened? 1 over n minus 1 is going to be larger than 1 over n. And Christian's telling me no. Okay, is it clear? That's what's happening. Since the denominator is larger, that's crucial. Denominator is larger. So 1 over it is less than 1 over n. Are you with me so far? That's why it is, because this is larger. So now, sigma an 1 over n diverges, smaller series is diverges, then immediately the larger series was also diverge. Okay, so that's to give you an example how really we use that. So the smaller diverge, it means the larger will diverge. So that's the comparison test. The difficulty with it is the difficulty we're facing. You have basically to find two things. You have to find what's less than it or larger than it, and you have to show inequality, which is make it a bit hard but very useful. Before we move on, I want to ask you two questions, and I really want your answers. So question number 1. The ordinary comparison works only for series with positive terms. So now I want you to do the following for me. I want you to give me series AN, BN, not necessarily positive, just to show you the importance of positive, not necessarily positive. Sigma AN converge, sorry, sigma BN converge, sigma AN diverge. Not necessarily positive. I want you to think of examples such that AN less than BN. Of course, we don't want them positive because if it's positive, that's nonsense. Where the larger converge, the smaller diverge. Who can think of, very straightforward example? I give you a little bit to think about. Please, I want all of you to give me the examples. If you don't know, write it, just mute and tell me what you think. Anyone? Two series, AN, BN, not positive, at least AN not positive. Sigma BN converge, sigma AN diverge. Who's ready? I guess I have to start giving 1 + 1 to everybody who gives me an answer on their quizzes. So you guys will start cooperating. Okay, you gave me one of them, Tim. I want AN. All right, I see what Tim gave me. So he suggested the following. He said, all right, take AN to be -1/n. Negative, and BN to be 1/n². Of course, AN is less than BN because AN is negative and BN is positive. There is nothing to it. Sigma BN converge because it's a P series, P = 2. But sigma AN is actually sigma -1/n. But last time we saw the minus is as a constant. We can actually pull it out, -1/n. But we know that this one diverges, so this is equal to -∞ at it diverge. So what's happening here, because the AN were allowed a negative value, they were able to go to -∞ and still be less than BN. However, when we put restriction to be positive, they cannot go down to -∞. They have to keep going over, up and up and up, and be bounded by the BN. So the condition positive is absolutely necessary in the ordinary comparison. The limit comparison is also necessary because the proof of it is based on the ordinary comparison. That's why it is needed. I want one more question from you. I want larger, more participation, please. If both are negative, can the comparison test be used? Yes, you have to be careful with it, Dr. You have to be careful with it. So you go to, no, I don't want you to use it when it's negative. That's the end of that. Yeah, don't use it when the terms are negative. Use them only for positive terms. Now, my last question is, I want you to give me an example. Again, simple one. Those are simple example. AN less than BN. And I want sigma AN to, what do I want? I want sigma AN to converge, sigma BN diverge. Just to show you that the test is very clear. Okay, again, you have a minute to answer my questions. And please, I want more participation from you guys. Okay, who's ready? That's my scenario. And I want participation. Okay, I want AN and BN. So what's AN? What is BN? You want me to pick? Okay, AN is 1 over N5. All right, definitely converge. BN, 1 over the square root of N. All right, is this a correct scenario? First, we have to make sure that AN is less than BN. So I have to convince you that does this property hold? Is AN less than BN? What's AN? 1 over N to the power 5. What's BN? 1 over the square root of N. Is this inequality true? And why? So the question is, does this hold? The question is this true? Is this inequality true? Is 1 over N to the 5 less than 1 over the square root of N? Yes or no? Please, I want answer on the chat. Okay, Maddie, yes, yes, yes. And let us see why. Why it is yes, absolutely correct, because the square root of N, this denominator is larger than the square root of N, because the denominator N5 is larger than square root of N. It means square root of N is actually less than N to the power 5. So when I flip them, I get 1 over N5 less than that. So it's so far everything is actually working well. Now, the larger sigma AN, of course, converges because it is a P series. That's P equal to 5. However, sigma BN diverges because P is a half. Okay, so every part of the theorem actually is required. So positive is required. AN has to be less than BN. So if sigma AN converge, sigma BN can converge or diverge, because if this one converges, this is larger. It can blow up to infinity. So if the larger converge, the sum of the smaller converge. If the smaller converge, the small of the larger converge. And that's what the ordinary comparison test is actually telling us. As I said, we will use it especially in cases where the cosine shows up, the sine showed up, because we have no idea how those functions behave. Otherwise, we will try to avoid them. So we will use them in sometimes, not a lot of times, but we should be fully aware of them. All right. Part 2 is the following. All the tests, I repeat what I said, all the tests we've used require the term to be positive. Ordinary comparison, you guys give me example. Limit comparison, it's hard for you to give me example, but it's totally based on the ordinary comparison. The proof of it that we omit in class is based on the ordinary comparison, as well as for the integral test. So now the question becomes, if the series have positive and negative terms, what shall we do? So we're going to start looking at this problem. Not very easy a lot of times, but we will take some special cases where it is possible. So today we're going to take a very special case of a series where the terms could be positive and negative. Very, very specific scenario. And the scenario we're going to take today is what we're going to call alternating series. So alternating series are very specific type of series that are obtained in the following form. So as I said, we're going to start looking at series where the terms could be positive and negative. All right. Today, the first special case, alternating. What's an alternating series? As the word alternating really suggests, an alternating series is a series whose terms are alternately positive and negative. Very specific format. So example, 1 minus a half plus a third minus a fourth plus a fifth, etc. So as you realize, the terms are positive, negative, positive, negative, positive, negative. That's what alternating series is. So another example is -1 plus 1 over that, minus, plus, minus. That's what alternating series. So the minute I give you a series which look like that, so for example, I suppose I give you 1 minus a half, minus a third, plus a fourth, for example, minus a fifth, minus a sixth. This is not alternating because the sign are not alternating. There's positive, negative, negative, positive, negative, negative. So this is not alternating. Alternating, it should be positive, negative, positive, negative, positive, negative. So it's absolutely crucial, the scenario. Now let us remember how to write those alternating series in sigma notation. We have to remember that. So we have 1 minus a half plus a third minus 1 over 4 plus so on and so forth. And let's see how I can write it in sigma notation. So this is a sum. Those terms 1 over 2, 1 over 3, this is 1 over n. There is no problems with that. And now I have those sign, plus minus. How we write this? Whenever you have plus or minus, we write them as -1 to the n. And usually n equal 1 to infinity. But I don't stop here because this n may not be always the right n. Let's see what I mean. If n equal to 1, I will have -1. If n equal to 2, I will have -1 squared, which is plus a half. So how can I manipulate this notation so that my sum will reflect that? Can anybody give me a hint? Anybody can, n -1, I'm having ideas, absolutely. Instead of n, I can put n -1. And this will do. So usually I put -1 to the n and then I go backward. I say, okay, does it fit the picture or doesn't fit the picture? Okay, so that's how in alternating series we can write them. So it's like -1 to a certain power n and -1 n plus 1 times a certain term, we call it the 1 over n. So with that, if I take the second one, -1 to the n plus 1 over 2 cubed. So I rewrite it so it will be clear. So -1 plus 1 over 2 to the power 3 minus 1 over 3 to the power 3 plus 1 over 4 to the power 4 and etc. So in sigma notation, this is going to be written 1 over n to the power 3. That's the easy part. And then I usually put -1 to the n from 1 to infinity, and then I check, does it work or not? If n is 1, I'm getting -1 over 1. If n is 2, I'm getting 1 over 2 cubed, it works. So you put -1 to the n and then you check your. So in general, in alternating series, in general, an alternating series will have the following form. -1 to the n or n -1, depending on the problem, where the bn are positive, and that's important. So everyone can, I can rewrite them. So it has the form, actually I can add sigma an equal sigma -1 to the n times bn, where the bn is positive. So let us see what I mean by the bn. So in my scenario here, the bn is the 1 over n. Those are the positive terms. In my scenario down here, the bn, by bn, I mean 1 over n to the power 3. In other words, where you can think about the bn is as follows. In other way, you can think about the bn, they are the absolute value of those terms. So in other way, you can think about them if they are the absolute value, which is the 1 over n. Again, here we can do the same for the bn. We can think of them as the absolute value of those terms. Now, there is an easy test. If you have a series that is alternating, it has to alternate. There is an easy test that tells us whether it converges or not. I will state it and we give an example. So suppose I have an alternating series. minus 1 to the n minus 1 bn. b1 minus b2 plus b3, where the bn's are positive. I emphasize that. The bn, as I said over and over, they are actually the value of the an. So if it satisfies two conditions. Condition number 1, if the limit of the bn is equal to 0, two conditions. And this sequence bn is decreasing. What does it mean decreasing? It means b1 larger than b2, b2 larger than b3, b3 larger than b4. So those sequence is decreasing. It means b1 larger than b2, b2 larger than b3, and so on. Then automatically we can say that the series converges. So the alternating series test, it works only and only for series that alternate. And it tells me that if the terms go to 0 and both conditions should be satisfied, and those terms decrease, so they go down, then we can immediately say that the series converge. Okay, let us practice this. And proof is actually very fun. I don't know if I have time today, I doubt it, but I would definitely like to show you the proof, because it's really actually very nice proof that you can visualize geometrically. So, but before we do that, let us see how to apply. Study the conversions of the following. Sigma minus 1 to the n over n. First, I want to make sure it's alternating, which is we know, but I would like to make sure. So I write up the first few terms. It's minus 1 plus a half minus a third plus a fourth, etc. So the bn here are basically, as I said, the absolute value of those terms. That's really what the bn's are. They are 1 over n. And now the question is, okay, does this satisfy both conditions? All right, so let's see, does it satisfy both conditions? Okay, so everybody, what do you think? Does it satisfy? Let's see it very easily. So we have sigma, minus 1 to the n times 1 over n. So my bn are the 1 over n. It means they are the absolute value of those terms. That's what the bn are. Do they satisfy both conditions? First, I immediately start usually with the bn. Do they go to 0? If they don't go to 0, we know it diverges, because the divergence test tells me if the terms don't go to 0, you're done. So we start with the terms. This is equal to 0, check. It means, doesn't mean it converges. It means that the first condition is satisfied. Now, what's the second condition? The second condition is going to look at the sequence bn. So I'm going to do it algebraically, but first let us see. Is the sequence bn decreasing? What's the sequence bn? What are we talking about? So the sequence bn are the sequence of the terms. So it means it's, if n is 1, so it's 1, a half, a third, a fourth, a fifth, etc. That's the sequence bn. Now, is this sequence decreasing? As I said, I will fully show it to you algebraically, but first I wanted to understand. Is this decreasing? Is every term smaller than the terms before it? Of course, it looks decreasing. 1, a half, a third, a fourth. That's definitely decreasing. Okay, but now let me show you algebraically how do you, in a way, show that it is decreasing. So it looks decreasing, of course, but now let us show it algebraically. So algebraically, why decreasing? So what does it mean? It's decreasing. It means if I take the general term, bn, which is 1 over n, and the term that comes after it, 1 over n plus 1. And the question is bn larger than bn plus 1? So that's algebraically what we do. Is bn larger than bn plus 1? Who can give me an argument why it is true? Because bn is 1 over n. Bn plus 1 is 1 over n plus 1. And I just mentioned a minute ago is that when the denominator gets larger, the expression gets smaller. That's really the idea. So because n plus n is basically less than n plus 1. So 1 over n is larger than 1 over n plus 1. So it means that Bn is larger than Bn plus 1. So that's how we show this algebraically. So the sequence Bn is decreasing. So now two conditions are satisfied. The terms become very small. And the sequence Bn is decreasing, so the series converges automatically. So this test only works for alternating. It doesn't work for anything else. Only for alternating, this is going to converge. All right, I'll give one more example, and I really hope to show you why it works, because it's actually interesting. It's interesting to see how the partial sums actually are behaving in this scenario. Try to look a little bit at the proof in the book, because I will use it, and tomorrow I'll just draw a picture, show you, convince you what's really the situation. Let me take another series now. So I will write it clearer and bigger for you so you guys can see it. So I have the following: sigma minus 1 to the n over to n plus 1, 1 to infinity. And again, here, that's alternating because those terms are positive. So minus 1 is just alternate the sign. So the Bn here are the n over to n plus 1. And the An means the terms of the series are the minus 1 over that. These are the terms. These are only, Bn is basically the absolute value of those terms. So we take them as absolute value. All right, does this one converge or diverge? What do you think? Okay, converge or diverge? Okay, let me see what happened to the Bn. Sorry. Okay, all right, what happened to the Bn? When n goes to infinity, it's n over to n plus 1. All right, when n goes to infinity, what's the limit of that? Okay, this is equal to, you can divide by n, both sides, so it's gonna give you 1 over 2 plus 1 over n. So as n goes to infinity, this goes to 0, this goes to 1/2. So the Bn are now becoming small. The Bn are becoming close to 1/2. So what does this mean? What can we say? Does it converge or diverge? So if the Bn converge to 1/2, it means the An, it means the term of the series, the terms of the series themselves diverge, absolutely diverges. I diverge for real. So it means if I take the original series, minus 1 to the n, so when n goes to infinity, the An, the limit does not exist, period. And let me say why it doesn't exist. Those terms become close to 1/2. So the minus 1 over n is going to have this effect. Some of the An become close to 1/2, some is going to become close to minus 1/2. So the limit doesn't exist, so by the divergence test, the series diverges. Okay, so this is an alternating series. It doesn't really mean it converges. We first have to check the general term. If the general term, the limit is not 0, which is in this case, actually that limit doesn't exist because the Bn are becoming close to 1/2, which is not 0, it means the minus 1 to the n, its effect on it is that making some terms close to 1/2, some close to minus 1/2, the divergence test tells me immediately that the series is going to diverge. Okay, so these are two examples of alternating series. So it's a very useful series, it is an important series, type of series, very important, but the test check their conversions is rather simple. Now, my last example, which is, I will go through it very quickly, but I hope you guys study it a little bit more. -1 to the n over n square. The Bn is n over n square. Now, does the Bn go to 0? Yeah, n over n square plus 1. Okay, this is, we divide by n square, I get 1 over n plus 1 over n square. The denominator, sorry, my mind went blank. If I divide by n square, and I think I divided by, what did I do here? Okay, as n, so I'll pick up a paper, and I think I have to fix this a little bit. It was too late last night. So the limit of the Bn is the limit of n over n squared plus 1. We know that this goes to 0. So if I divide by n squared, I will have 1 over n, 1 plus 1 over n squared, which is, of course, equal to 0. Now, the only hard part here is that the n is n over n squared plus 1. It means if I take the sequence, it means not very clear. 1 over 1 plus 1, 2. 2 over, so if n equals to 2, I will have 5. 3 over 3 squared plus 1, 10. So it's not very clear. I mean, it is going to be decreasing, but it's not very, very obvious how to show it is decreasing mathematically. But there is a trick that use calculus 1. Okay, we can look at the function x over x squared plus 1. So what is f? And we show that it is decreasing. And what is f? So we construct a new function, f of x. So here my Bn is n over n squared plus 1. So I take my function f of x to be x over x squared plus 1. If this function decreases, it means if I can show this one decrease, I can show that the Bn decrease. Now, how to show that a function decreases? Okay, calculus 1 tells me show that the derivative is negative. Okay, so exactly that's what we're gonna do. We take the derivative, we find 1 minus x squared over 1 plus x squared. But I'm only interested for large values of x. I'm not interested for x is small. So if x is bigger than 1, this is going to be negative. So now Bn is decreasing because Bn is f of n. Bn plus 1 is f of n plus 1. Since f decreases, f of n is bigger than f of n plus 1. It means Bn is larger than Bn plus 1. So this is a trick. If you cannot show it very easily, it decreases, like problem number 1, we can, use some basically harder technique. So by the alternating series test, the series will converge as well. Okay. All right, tomorrow I will start by showing you why this test works, and then we're going to move on to another test that help us also to study the conversions if my series have, where in 2 cases where I cannot use limit comparison, I cannot use integral test, that's really the hard part of it, and if my series have positive negative terms, it works at all. All right. Any questions before I go? Anybody? Okay, so remember guys, I have office hours, and none of you is showing up, but I do have office hours. I keep back and forth checking you, and I don't see anybody. Anybody who needs help, please feel comfortable to join me in my office hours, which will start basically in 5 minutes. All right, please do your homework for tomorrow and come at your office hours the same time on Fridays. No, the office hours on Fridays are before class, because that's when you guys need help. And I also have the URL for Friday's office hours. So you join me before class. Any other questions? Okay, stay safe, guys. Make sure you stay safe, and I'll talk to you tomorrow. Bye-bye for now.